Neural networks can be fooled by changes that are so small that humans can't even tell the difference. And what's even worse is that these changes are created by using the model's own gradients. What I'm going to be going over is how adversarial attacks work, and then how I added my own attack and training so that my model would be more robust against certain attacks. In this image, we can see that if we took an image into the neural network and we added some sort of permutation to our image, so some slight changes in pixels, either shifted to the left or to the right, we would have an image that comes out and it would recognize this image as something entirely different. We might think that this would come through as an airplane, but due to the extra permutation and loss that has been added to this, we find that this could end up being a dog, or it could recognize it as something entirely different. If in this image we had a higher resolution adversarial example, we might see that the image just looks more pixelated. There's in the sky slightly different colors, maybe some reds, maybe some greens that are just look like extra noise. But the model, since it goes through and looks at things on a grid basis holistically, the model can be tricked rather easily. And my project goes over the CIFAR 10 object class recognition. And so this model is not going to be a huge model going over every single type of image recognition, but using adversarial attacks in this is easier because we only have 1 through 10 as our possible answers. This model already works and it gets about 70% accuracy on a clean image test. So we can see here that if I were to go and upload to my file some sort of screenshot, and if I did an upload and predict, we could see that it thinks that it is a ship based upon the value that's returned, and it's about 70% confident. In the example of adding an adversarial attack, what this really is this is an exploit to the neural network that uses gradients. And if that gradient can tell the model how to, if you will, improve or make a change that allows it to think the image is something else, that's how you can break the model. Really, all you have to do is change the model's input slightly so that it increases the loss. And what you can eventually have is an image that looks similar enough to a human to where this might even get past some sort of human verification, but to the model, it's a completely different object. So in this diagram, we have our image that goes into our model, and we can see again that our loss is down by quite a bit after this fast gradient method is applied. What we get is really this noisy image, essentially. And this is a very common exploit that can be done in image recognition. What what FGSM is the fast gradient sign method. That's the general abbreviation that is used for it. And what it does is you can take the gradient of loss based upon your input image and then take the sign and add a small epsilon. That's all that you have to do, but this simple equation is enough to cause the image or model recognition to be completely different. This can be done in multiple different ways by adding in what I will show later to be like a patch on an image so that the model gets tricked to learn what that patch is rather than what the image actually is. So that's another kind of similar fast gradient method that can be used. And in the code for this, it's really just one simple thing that we're doing in our attack. We take our epsilon across the images that we are scanning, and we apply that gradient sign method. And what we do is we add our permutation after the fact, and what we return is this attacked image, essentially. Most models have their own way that it is trained, and since these models are trained similarly, these attacks can be done to many different models, being that they are trained similarly if you don't have any sort of checks for adversarial attacks. Before adding any defenses, I evaluated my model under an attack. At epsilon value 0.03, which is a very small, almost imperceptible value, the accuracy collapsed. That's a normal part of doing adversarial attacks, and it is expected if there is no sort of checks that are in place to prevent these sorts of attacks. The standard training does not prepare our models for adversarial inputs. So we can see here in the terminal that after doing some adversarial robustness, we can see that based upon our epsilon value, our value of 0.3, which was our initial test, actually increased by about 20 to 25%. That's a rather big increase for a model. And we can see here using different epsilon values have their own percentages. So an epsilon value of 0 is essentially a no attack. And then the other epsilon values here are different weights of attack or different strengths of the attack. The simplest form of training is adversarial training. So instead of trying to train just on clean images that don't have any sort of changes to them, you can also add in adversarial versions of those same images. It means that the model gets to see both during its training, and it generally leads to more stable decision boundaries. This changes the loss function, and changing the loss changes the behavior of the model as a whole. We can see that in training, when we put in our convolution, we put in clean images as well as adversarial. As that goes through the pool of decision making, eventually we have our loss output. And we can see in our code example, we have under the training, our loss ends up becoming a total running loss. This is for our loss of clean and advanced, or our adversarial rather. This gives us slightly different loss values than we may otherwise expect. Looking at the terminal, previously, before any sort of adversarial attacks, loss started at about 1 and ended at about 0.3. Due to adding in adversarial attacks, the model is now a lot less confident in its decision making. This is due to adding these adversarial attacks, and that's sort of a normal thing that will happen. Your model is going to become less confident because it's getting images that are harder to recognize for the model. Our robustness that we have in the model, it slowly gets worse as an attack gets stronger. As we hinted at before, our epsilon value of 0 is no attack taking place. We can see that the model is pretty strong. It does fairly well at recognizing images. What we do see that as we are adding in attacks, the model is getting worse and worse with the strength of those attacks. So this same model, there's nothing being changed besides just giving it more and more harder tasks to define. That's just increasing the bar of this model. What we can see here is after our training, we end up having a slightly worse clean accuracy. Our accuracy drops a little bit. Our training is dropped a little bit as well, which is to be expected being that we're doing adversarial training too. But our accuracy of adversarial attacks has increased dramatically, going from a 10 to 20% chance to a 46% chance. That trade-off gives us some robustness versus our hypothetical raw accuracy in the real world. So this is something that happens not usually in testing when you're first creating your model and you're truly giving it good examples to learn off of. But it happens in the real world when we're dealing with security, when we're dealing with vision, or any sort of safety critical items. You have to take this robustness trade-off into account. Some of the options that we have with adversarial training or ways to prevent attacks is our adversarial training that we went over. We also have input preprocessing, which is cleaning or transforming our inputs to remove any sort of this noise that we added through adversarial training before it gets to the model. So this could be like compression or any sort of resolution issues that we might be having. So think of like a 480p sized image versus a 4K sized image. That 480p sized image, when blown up to scale of 4K, has a lot of noise in it. And it could be things that it's just wrong for those different pixels in the 4K upscaled size. And so you can sanitize those before it goes into the model. You can have other models that are looking at your model's input and output to detect these sorts of anomalies. But most of the time, what we do is we make sure that we have some sort of adversarial training that goes on, as that's our best chance to train our model. And we also do some sort of input sanitization so that we can make sure that we're not giving it bad input. So adversarial attacks show that machine learning isn't just about your accuracy. There's other trade-offs to consider through this, like your robustness, when you're getting into the real world examples. It's about understanding how your model is working under stress. What I'm going to continue to do in future videos is going over how stronger architectures and more advanced defenses can build upon this foundation and make your model even stronger. I hope that you found this useful and that you learned something about adversarial attacks.